All right, so this lecture over 14.3 is almost more like a reading guide, but I'm going to make it a lecture, and we'll just go through it together. What we're going to start with here is a drawing of simple harmonic motion. And before we start drawing anything, I guess we'll start by labeling some time values. We know that this time is going to be 0 up here in the for each step here. We're going to have a mass on a vertical spring, and so let's go ahead and write these in. This one's going to be 1/4 of the period t for that time. This one's going to be 1/2 of the period. This one's going to be 3/4 of the period. And finally, in step 9, the time will be back to the beginning of the cycle, or will be 1 period. So we expect our position to be back to where it was when it started. In terms of theta, we're going to think of this the cycle as being once around a circle, and if that's the case, then we'll have 0 radians right here. Should we write radians? I'm going to. For a quarter of the period, we know it's going to be pi/2 radians. And the reason for this being that once around the circle is 2 pi radians. So if we are halfway there with half the period, we expect to be at pi radians. At 3/4 the period, we should be at 3/2 pi. And then finally at 2 pi radians when the period is when the time is the period. Okay, so that's what we have here, and that's not stated in the book, but I find that it helps students to think of it in terms of radians right off the get-go, instead of in terms of time based on the period. It's going to help make sense of these sinusoidal graphs that we're going to make. So the next part here, I want to do a drawing similar to what's in the book, and this is once again on page, I can write that down, page 443, in case you want to just look at what their drawing is and not do exactly what I'm doing. But I'm going to draw this sphere. Looks like it's an orange sphere, and at these locations, we're going to consider where the middle of the sphere is. So at time equals 0, or at 0 radians, the middle of the sphere is going to be right at this dotted line here. This dotted line is y equals the positive amplitude. This dotted line is y equals 0. And maybe I think I already have this here. I already have it written on here. That's nice. And so you can see we're going to match the sphere up with those points, right? And once again, this is an object oscillating back and forth that we're drawing here. So the object is now going to be at 0 at pi/2 radians, or a quarter of the period. And then the object is going to be at a negative amplitude at half the period, right? At half the cycle, or at pi radians. Then it's going to be back at equilibrium at 3/2 pi radians, or 3/4 of the period. And then finally, it's back to where it started, the original position, at time equals the period, or 2 pi radians. You can see that this is the shape of a cosine wave for its position, and a positive cosine wave. All right, so let's go ahead and add a little more to the drawing. We know that these in-between steps at 2, 4, 6, and 8, we can say that the object is going to be, it's going to be somewhere in between these dotted lines. We don't know exactly, but I'm just going to go based off the text, and it has the object right here. So not halfway in between, right? And that is correct. It won't be halfway. And then right here, And then I believe this one, yeah, will be just on the other side of the dotted line. So similar to that. Once again, this is in the book if you need to look at their drawing because it's better. Okay, so let me see. Try and add a little color here. Give these spheres a little shape. It's like art class. All right, so there we go. Then we'll add in the vertical spring, which is going to be from above, and it's attached to the ceiling here. So we expect it to be the most compressed here and in here, and then further compressed, or not as compressed at these other spots. Obviously, it doesn't have to be perfect. We don't expect it to be, but you get the idea. Okay. Good. All right, I'm going to go ahead and pause it there for a second, and then we'll come back and get the sine and cosine wave. All right, so one thing we forgot to add here was the velocity vectors for this object on a vertical spring. And so I'm going to switch to green, and this is just like in the textbook. We can see that at this first position, the object is at the top of its oscillation, so it's not moving. And then as it drops to the second position, it now is going to begin to move with a negative velocity because it's pointed downward, albeit a smaller, not its max negative velocity. That will happen right here. When it's at equilibrium, it is traveling its max speed. This is as fast as the object's going to go because the object's going to go up and down, back and forth, right? And so at this point right here at 3, right? And you can see the 3 at the top there. This is the max speed right here when the object is at equilibrium. So what we're seeing is that when the object is at position 1 right here, right? It is at positive amplitude. And you can see that from over here, right? Y equals positive a. That its velocity here is 0. But then when it's at position 3, it's at max negative velocity. And then as it continues downward, its velocity vector is still going to point, whoops, I was going to stick with the green there. Oh no, that's not good. Let me see if I can redo that. It's still going to have a negative velocity, but it's going to be smaller again. And then finally, it's going to have a velocity of 0 at position, what is this, 5? And then from position 5, it's now at the furthest it's going to go in the negative direction, which is y equals negative a, or a negative amplitude, compared to equilibrium, right, where y equals 0. So then it's going to start moving upwards from here, just like that. And then when it gets to here, it's going to reach its max speed again, but this time it's going to be its max positive velocity. And so I should draw the size of that similar to position 3, but obviously pointed in the other direction. And then when it gets here to position 8, it's still going to have a positive velocity pointed upwards, albeit smaller, and then finally getting to 0 right here. So we see that v equals 0 right here. This is another stop right here, and another stop right here, right? And so anyways, we want to now take that and then draw its position versus time graph here. And what we're going to see is that this is sinusoidal motion, that this is a cosine wave. And what we're seeing is the object starting right here at time equals 0, that it is going to be at its positive amplitude, right, at position positive A, which is right here at time equals 0. And then as the object moves downward, right, it's going to move to this position, to position 0 at time equals a fourth or a quarter of a period, right? And the reasoning for this is that well, we know that to be true, but how it moves there isn't going to be a straight line, right? It is accelerating through this motion, right, in these first two parts. It's actually, it always accelerates towards equilibrium. So we expect to see a large negative acceleration at position 1, and then 0 acceleration at position 3. So let me go ahead and write that in. I'm saying that when the object is right here, this is at position 1, this is max acceleration, and it's going to be negative. And then at position 3 here, the acceleration is going to equal 0. So notice when the velocity or the speed is at a maximum, right? The max negative velocity at position 3, the acceleration is 0. So the acceleration is based on is the acceleration back towards equilibrium. When the object is at equilibrium, as it is in position 3, there is no acceleration. So we know the same thing will be true at position 7, right? That the acceleration here will also be 0. We also know that, so I can, if I drew the acceleration vector, I could draw it right here. It's a max negative acceleration right here. And that means that at this point right here, the acceleration equals a maximum as well, but it's going to be in the positive direction. It's going to point up. So that vector, or that acceleration vector, would point upwards like that right there at position 5. And then finally, when it gets back to position 9 right here, right, once again, the acceleration points towards equilibrium. So it's going to point downwards here, and we can say that acceleration equals a max, and it's going to be negative, and we can draw that vector in right there as well. So we're noticing some changes in acceleration, and I know we didn't account for the other positions, but I can do that really quick if you like. I just was trying to draw these acceleration vectors, or not confuse them with the green velocity vectors. But you can see that when the object is located above 0, that the acceleration is going to be smaller, but it's still going to point towards equilibrium. And then once the object gets past A equals 0 here at position 3, then it's now on the other side of equilibrium, right? Because where the heck is equilibrium? Are we having a hard time seeing that? Let me go ahead and give that a dotted line. This, and I'll go ahead and put it in yellow. This is equilibrium, right? This yellow dotted line. All right, so what I'm trying to say then is that when the object passes the yellow dotted line and is now right here, it's going to have an acceleration directed towards equilibrium. Now, it's not a maximum, but it's still present at position 4. And then when it's at position 6 again, once again, it's still below equilibrium, or below the yellow dotted line. So once again, its acceleration is going to be towards equilibrium. And that's what way you can think of it, right? Because even though the velocity vectors at position 4 and 6 are completely different, the accelerations are actually are similar, right? Are the same, because it's going to point towards equilibrium. It's based off the force back towards equilibrium, and the force spring equals kx, so or negative kx, or however you want to say it. So anyways, so right here then we see there's an acceleration towards equilibrium, and then finally a max acceleration towards equilibrium at position 9. Okay, so hopefully that's making more sense. The red vectors being the acceleration and the green vectors being the velocity. So what these sinusoidal waves are that we are going to draw here are going to represent the x versus t, well in this case y versus t graph, the v versus t graph, and the a versus t graph. And they are going to be sinusoidal waves. This first one starts with the position being the positive amplitude, so it's going to start up there. And we know that when the sphere gets to position 3, when it's at equilibrium, that this is going to create actually a cosine wave. And the reason for that being that, well, what is the cosine of 0? We would say positive 1 for position 1. What is the cosine of pi over 2 or 90 degrees, pi over 2 radians? We would say 0. So what we see here is something that looks like this, right? And that the object is maybe right there if we were making the cosine wave for position 2. I don't really care about position 2 as much, you know, but position 1 and 3 are very particular, right? At position or at time 0, the position is the positive amplitude. So what I'm trying to say here is that the graph is going to end up looking something like this, and by the time we get to position 5, right, we expect it to have a negative amplitude. So maybe something like this right here for position 5. And then for position 7, it's back at equilibrium, so maybe something like this right here. And for position 9, it's all the way back to, it completes a cycle and is always all the way back to where it started, is back here. So our graph is going to look something like, it's going to be a positive cosine wave. Something like that. Not a perfect drawing by any means, but something like that. So what we're saying then is, or what we used there was that we called this time right here 1/4 the period. We called this time 1/2 the period. We called this time 3/2, or I'm sorry, 3/4. My bad. 3/4 the period, and we called this time right here the period. And we could also think about those in radians if it helps make more sense, or if you like that better. So we said we called this pi over 2 or 90 degrees, pi over 2 radians. We could call this point right here half the period. We could call it pi radians. We could call this next one 3/2 pi radians. And finally, we could call this last one 2 pi radians. And that first one, pi over 2, that's the same as 1/2 pi radians. So if you'd rather write it that way, maybe it's a little easier than pi over 2 radians to think about. So let me just rewrite all of that and bring it a little closer there. All right, so something like that right there. And so this is kind of the idea, right, that a sinusoidal wave represents the position versus time curve for simple harmonic motion, for an object with a linear restoring force. And so coming over here, we recognize this as a positive cosine wave, hopefully, from our practice we did in class. And the equation for x versus t, I wasn't planning on doing this yet, but maybe we'll come back to it. Let me go ahead and just jot it in, and maybe I'll come back and reference it later. So what that equation will be, let's go ahead and write that in blue here. And that is going to be x of t is equal to our position as a function of time is equal to A, the amplitude, times the cosine, times 2 pi, the frequency, times time. And we'll talk about what those mean, 2 pi ft, but I think it's just a fancy way for us writing theta. But it's in terms of t, right, and the frequency. So, all right, so good. Another way, or another thing I guess I want to mention is that if frequency is the same as the period, we could have also written x of t is equal to a cosine 2 pi t over the period. All right, and this also would work. Good. Okay, so either of those would have been fine. The velocity wave is going to be different. And what do I mean by that? Well, let's look back up at our picture here. We see that at the start, the velocity is going to be 0. And then, and it's going to move by step 3, right, or pi over 2 radians, or a quarter of the period. By step 3 here, it's going to be at a maximum, but not just a maximum, a negative maximum. So we know that we should start at 0 and move to a negative max velocity. So our wave for this, our sinusoidal wave, is going to start here, and then by 1/4 t, which we should probably label, and 1/2 t, and 3/4 the period, and the period. And we can also write it in terms of pi if you prefer. That this sinusoidal wave is going to start at 0, and by the time we're at 1/4 the period, we're at step 3, we're at max negative velocity, right? That green arrow is as large as it's going to get, and it points downward at step 3 there. So what I'm saying then is we should be right here, and we're going to need to create a sinusoidal wave that approaches that. So this is going to look like a sine wave, but be, not a huge fan of that straight line it was giving me. Let me try that again. It's going to look something like that. And so this is a, I think let's draw a little bit more, but we can see it shaping up to be more like a sine wave, and in fact a negative sine wave. If we go back up to our picture here, we can see that from step 3, when it's at max negative velocity, and as it approaches step 5, it's going to be at 0 velocity again. So by the time it's at step 5, which is pi radians, or half the period, it should be at 0 velocity. So we're seeing that this is indeed looking like a sine wave, albeit a inverted sine wave, right? A negative sine wave. And so from there, at 3/4 the period, we're back at max velocity, but now it's positive. So we expect to go up to, let me see if I can get this in the picture better. We expect to go up to right here. And then by when we completed one full period, or 2 pi radians, we now are at 0 velocity again. So we should be back here at 0. So our sinusoidal wave will continue like this and end like this. And you might say, well, this looks awfully similar to a cosine wave. And yeah, that's the idea, right? It's just a shifted cosine wave as a sine wave, and it just starts at a different point, right? That's kind of the idea. And anyways, So this is a negative, let's write this in here. This is a negative sine wave that we're dealing with here. The equation for this, once again, this is going to look a little rough, but that's okay. We'll just kind of go with it right now. I'm going to leave it as v of t. I guess I could write x or y. I think that in the book they have this as x, so I'll go with what they have in the textbook right now. And which is interesting because this is all about y right now. So I'm just going to not write that on there right now and just realize I think it should be about y because we're obviously dealing with the y direction. I guess we'll go ahead and we did have x of t in the last one. I see. So maybe we should correct that. Let's make it all about y. And we'll call this Vy of t. We really don't care about the x direction right now. But it could be the x direction for another object moving left and right instead of up and down. So it's not a huge deal. Is equal to negative V max. Notice the negative sign because this is an upside down or a negative sine wave. And times the sine of 2 pi ft. And we know that 2 pi ft could have been written 2 pi t over the period like we did up there, but we're not too concerned with that. Let's also write an expression for V max. V max is equal to 2 pi f times the amplitude. Now, if I think what you can see, if you know calculus, that this is the derivative of the position function, right? That is the velocity function. So that is why we have had to flip the wave and make it negative or invert it. That is also why we end up with this 2 pi f out front for V max, right? We can see where this expression is coming from. The A is still there because A is just a constant hanging out front from the position wave. If you don't know the calculus for that or you don't know what a derivative is, don't worry about it. I'll kind of go into this a little later, but you can see maybe some shortcuts if you do know calculus. All right, so good. And even if you don't, right, realize that we're creating these sinusoidal waves just by looking at this picture, right? You can always just go back to the picture and just figure it out, right? You don't need calculus to do that. You just go back to the picture. What's the acceleration doing? Let's do that right now. Acceleration at the get-go is a maximum because it's super far. The force is proportional to the distance away from equilibrium. You are very far away from the yellow dotted line. So the force is a maximum back towards equilibrium. The acceleration is a maximum towards equilibrium, and it's negative, right? Because it's pointed downwards. So let's go ahead and add that in. So we have a negative A max right here to start with at time equals 0. Then what's going on at half pi radians or quarter of the period? That's step 3. We can see the acceleration is now equal to 0 because the object is at equilibrium. So when this happens, and the acceleration is now 0, so we're expecting something like this right here. Okay, let's keep going with this and just get these key points, and then we'll draw our wave in. Then finally, at pi radians or half the period at step 5, we see the acceleration is now at a maximum again, but it's pointed up towards the yellow dotted line. So we expect a max positive acceleration at half t, right? So we're saying that at right here, we should be at a maximum. And I did forget to write in, like I did earlier. Let's go ahead and jot those in real quick. 1/4 t, 1/2 t, 3/4 t, t, and then let's write in I want to do this in purple. That way it all looks the same. This is half pi radians, 3/2 pi radians, and 2 pi radians. All right, so just going up a half every time in pi radians. All right, so let's go ahead and draw. So what's going on at 3/4 period, right? Let's get these other couple dots and 2 pi radians. Well, at 3/4 the period, the acceleration now is back at 0. We can see at step 7. So let's go ahead and add that dot in here. And then at 2 pi radians, or 1 full cycle, we do expect that the acceleration, or we can see since the object returned to its original position between 1 and 9, right? The orange object is back at the top. We can see the acceleration is also returned to a negative maximum. And that should be obvious by looking at 1 and 9 and the red arrows being the largest and pointed down. So, all right, so a negative maximum. Okay, so it's back here. Okay, so if we look at this then, this, and we realize this has to be simple harmonic motion, this has to be a sinusoidal wave, so we'll draw it like such. But we can see, oh, my sinusoidal waves are kind of garbage. All right, so I'm not a math teacher, so that drawing is not ideal. But you can see that it is one of the types of waves that we had before, but flipped, right? In which it's an inverted one of these. Which one did we just invert? Was it the position function or the velocity function? And what I mean by that is, well, look, at the position function, you started at positive A, or a positive maximum, and now in the acceleration, you're at a negative maximum. So you can see that the acceleration wave is an inverted position wave. And that's important to realize, because that's always going to be true, is that the acceleration graph is going to be an inverted position graph, and the position graph is going to be an inverted acceleration graph. And so that's a good shortcut to remember. And so let's go ahead and label that then. So this is an inverted cosine wave that we have here, so also known as a negative cosine wave. And that should make sense, right? Because you can always check with your pi radians. And because the cosine of 0 is 1, right? And that would be for a positive cosine wave, but for a negative cosine wave, it's the flip. So the cosine of 0 is -1. And then from there, it returns back to 0 because the cosine of 90 is 0, and that's what we have here. I was thinking about this with if you were thinking about it in terms of radians, you could call negative A max, you could think about it as starting, instead of at 0, at 180, right? So starting at pi radians. So having 0 be pi radians and the quarter t be 3/2 pi radians, if that makes sense. And that gives you that shift that you want for this graph. And I think that might be the most appropriate way to think about it, to be honest. But anyways, okay, so let's go ahead and jot this equation down right here. So this is going to be AY of t. Our acceleration in the y direction as a function of time is equal to negative A max. That's an A, that looks kind of weird. Times the cosine of 2 pi, the frequency, which is really just 2 pi f is omega, right? So that's omega, or angular velocity times time. And so that's why 2 pi ft is really just an expression for theta, or angular position. Okay, so then what is A max? Well, A max, and once again, if you know calculus, you can kind of make sense of why this is. If you don't, well, we'll make sense of it later. But we can see that A max, let me write it right up here. A max is equal to 2 pi f squared times the amplitude. And finally, these last two questions, where is the object located when A equals 0? If we go back up and look, we see that the object is at the yellow dotted line. Oops, I can't seem to zoom in here. There we go. Is at the yellow dotted line when acceleration is 0. And acceleration is at a maximum when it's at an amplitude away. So where is the object located when A equals 0? We can say at equilibrium. This is, of course, new equilibrium. And then when, there should be an N there, A equals a maximum, we would say, well, this is when the object is displaced the maximum displacement away, which is an amplitude. So we could say at an amplitude from equilibrium, at the amplitude. Okay, because obviously it's a max acceleration when it's at the very highest point or the very lowest point, but the acceleration points in different directions. Okay, so there we have it. Hopefully that makes sense, and I'm trying to draw some connections there with your math class based regardless of how much math knowledge you've had, and yeah, hopefully that's making sense. So we'll go ahead and try to explain these equations now on the right and make some sense of them. All right, so let's go ahead and look at this next page. And we have angular velocity being omega. And we want to write it in some different ways because we're going to see omega expressed differently here. So right off the bat, it is angular displacement divided by, or the change in angular position, which is angular displacement, divided by the change in time. And so this is angular velocity, or omega. In terms of if once around the circle is 2 pi radians, so if that is your change in angular position and you divide that by the time it takes to go around the circle, that would be the period. So there is another expression for omega, 2 pi over t. And then finally, and you don't always have to write the radians there either, but I'm going to. Finally, you have 2 pi if period is, or 1 over the period is equal to frequency, right? So if that's true, then we can just make that substitution in here. And so, and get that final expression for omega, or angular velocity. Okay, so hopefully that makes sense, and that all rings a bell because that's kind of review from circular motion a little bit. All right, so what we have here is the idea that simple harmonic motion for one object allows us to understand simple harmonic motion in general for multiple objects. And whether it be a mass oscillating horizontally, vertically, a pendulum at small angles, this is actually going to be, and you can think of this like a coffee cup in a microwave. And here you have your cup of coffee. I don't know if you can see that. I don't think I made it any better. Right here, this circle. This is your cup of coffee, and it's moving about a microwave, or the mug of coffee, and it has an angular velocity like this. So it's rotating counterclockwise. And then you take a light source and shine it from this direction, right? And these are just light rays that are going to hit this mug of coffee and create a shadow. And you can see the shadow. Let me go ahead and let me put that in yellow. The shadow right here on the wall moving. And this shadow is going to oscillate about an equilibrium position, right? There's an equilibrium position right here, this purple dotted line, right? And the shadow is just going to oscillate back and forth from a positive x value to a negative x value. And so what it's going to look like is a mass, a horizontal mass on a spring, and it's going to behave the same way. And we're going to be able to draw the same relationships from this. So that's what we have here, and that's what we're studying and looking at. All right, so first off, starting off with this first diagram we can see that the cup of coffee is a distance. Let me distance of an amplitude away currently, right? But we want to know its position in the x direction. We have two directions here. We can see the amplitude could be split into an ax and an ay, right? This would be the ax, and this would be the ay. And we just want to describe its position. So really then what we want to do is solve for ax, right? Okay, so it says resolve the amplitude and components, proving that its x component is equal to. Well, if we look at this is a right triangle. And this is my hip. This is then my adjacent. And it looks like our angle theta. Well, it's not theta, right? It's actually phi or phi. Our angle phi is right there. And so we can see then that our relationship there is that the adjacent is equal to the hip cosine phi, right? And that's just using a little SOHCAHTOA there. So we can say then the adjacent, which is ax, so we might as well just call it ax, is equal to the hip, which is the amplitude, times the cosine of phi. All right. So what the heck is phi, right? And maybe we should put a box around that. Let's just save that for later because we're going to need that expression here shortly. But what is phi in terms of omega and t? Well, we know that omega is equal to the angle over time, right? This is like speed equals distance over time. So we can just rearrange this, right, and solve for phi. Phi then is equal to omega t. Okay, so go ahead and write that in right here. Then they say, what is omega in terms of radians and frequency? And we just did this a second ago, right? We said that omega equals 2 pi radians times the frequency. And I didn't write radians in, but that's okay. All right, so that's good. And then finally, what can we say here? Well, let's sub, right? Let's sub this in. So I'm saying we'll take this right here and sub it in right there. And so if that's the case, then we can write that omega, I'll just write sub right there, or not omega, I'm sorry, phi is equal to 2 pi f times t. So throughout these problems, we're going to see 2 pi ft, and I just want you to remember that that's phi, or that's theta. That's the angular position, right? That's what we're dealing with here. We called it phi in this case, but yeah, it's theta. It's an angle. So so really, when we were taking the cosine of phi up here, right, we were just taking the cosine of an angle, right? And that's kind of the idea that I wanted to get across here. And instead of, but we're now going to sub in for phi 2 pi f times t. So we're going to write the expression like this, remembering that 2 pi ft is just an angle theta or phi. So we have the position as a function of time is equal to the amplitude times the cosine of 2 pi f times t. Now you might say, well, why go through all that hassle, right? Like, why can't we just leave it as phi or theta? Why do we have to write 2 pi ft? Because what's going to happen is, in some of our problems that we do, we're going to want to know the position of the object based on the frequency and the time and the amplitude we're given. We're not going to know an angle or an angular position, right? We're not going to care about that. We're going to be like, look, it's simple harmonic motion. The amplitude is this. The frequency is this. What is the time? Or what position is the object at? Here's the amplitude. Here's the frequency. Here's the time. And so that's the idea. That's why we can't just. That's why we need this other expression for the angle, right? Because we want to do more with these equations than be limited to just an angle. So we have this expression right here, and subbing in for the angle, and it allows these equations to work a lot better. So we can say, just a reminder here, that the amplitude, which is A, right? This is our max position. So x max is A, is the amplitude. Okay. All right, so hopefully that's making sense. And now if we look back, we can see, well, this equation right here, right, that we just wrote, is this equation right here, right, that we had from our position versus time curve. And here it was y of t, but x of t is fine, and it doesn't matter, right, if you're describing the vertical or horizontal position. And what else I want to say? I think that's about it. So something to realize, and I think this is important to bring up, is that the cosine function is not does not have to be the position function. So I know in the book that they use cosine functions for the position function twice, but you could just as easily have a sine function for your position function, right? Like, why can't the object start right here at, let me see if I can draw this in some new color. Let's see, purple. No, we already used purple. I guess this light green I haven't used. Why can't the object start here and then do something like, this my sine wave looks terrible. Let me try that again. So why can't the object hit a maximum right here and then do this, and then do, whoops, we're not getting the curve again. I don't know why that happens. So why can't we get a positive sine wave for our position function? And we can. So this green line would be a positive sine wave. And you can see it's just a shifted version of the cosine wave, right? And just starting at a different point, starting at 0 and moving upwards, this is just as likely to happen. And then You just would change the location of the initial location of the object, and everything would be modified slightly, but it's all the same type of motion, simple harmonic. All right, so anyways, coming back down here, let's go to the next page. So this coffee cup, right, it's going around the, the microwave. Okay, so it's right there. And it has a velocity that is tangential to the circle. And we can see that velocity right here. Let me go ahead and highlight it in green. All right, so it has this tangential velocity, right? And we want to be able to describe that. So over here, in terms of omega and r, we realized that we learned that if we multiply the angular velocity by the radius, we get the tangential velocity. So we can write this as omega times r. And then if we take it a step further, remembering what omega is, right, in terms of F and in terms of A, right, because we did have an expression for omega, right, I'm sorry, omega in terms of radians and F, and then remembering that the radius, right, R, is actually equal to the amplitude, and that will give us our capital A. We can go ahead and, so what I'm trying to say is we're going to sub in amplitude here, and we're going to sub in 2 pi f radians, right, there. And we can just write this as 2 pi frequency times the amplitude. Okay, so here we have an expression for our max velocity. And we're going to see this show up later. Okay. Now we realize that this coffee cup, we're interested in maybe its x velocity, not its max velocity. But this is its max velocity right here. So is v in the drawing tangential? I'm not sure why I'm asking this question here, but apparently I felt it was necessary. Yes, it is. So we want to know the x velocity, the x component here. And this is tricky because you can see it's going to have a negative x component, right? Because to the right is positive and to the left is negative. But what I'm trying to say is we're going to split this. And what I drew right there is actually what we want, that first vector. It's going to create a 90-degree angle, but what the heck angles am I working with here? Because phi is hanging out down there, and we'll make phi this pink angle right here. How do I, where is that angle up there, right? So this is some different angle. We'll make that a double angle. Okay, and if that's the case, this is 90 right here. So this double angle, maybe we'll give it the color blue. Okay. So then this angle right here, if we think about it right here, let me see if I can add some color. Oh, geez. That pink highlighter is just, it's just a little too much. I think it's the size of it. Anyways, if that's the case, then check this out. See if you can follow this. I'm saying then that, let's see, this would mean that this is the double angle I was talking about, the double lines, and this is in blue. So that, hopefully you like that, that makes sense, and that this is, that this angle right here, whoops, not in blue, let's put that in black. This angle right here is our is phi. All right. So what I'm saying, let me see. Ugh, I just made it a little bit even grosser to look at. All right. So that's kind of where we're at, and so my point here is that we can call this Vx right here, this red dotted line. Whoops. Ooh, I think my eraser's on. Okay, so Vx is an opposite. Hopefully you can see that, and that is making sense because it's across from that pink angle phi. Okay, let's go ahead and maybe draw it over here. So what I'm trying to say is this. This is Vx. This is Vy, we don't care about it. This is 90 degrees right here. This is the pink angle, and this is the blue angle we don't care about. Right? And so all I'm doing is trying to take this little tiny triangle that kind of was green and the red dotted lines and just redraw it right here, right? And so I can use the green highlighter. This is the green part right here. This is the velocity tangential, and that's the maximum, right? That's V max. Okay, I guess I probably should have used just black. All right, so anyways, this is the pink angle. And this is the pink angle is phi. That's all we were trying to do, because I want you to see that Vx is an opposite and Vy is an adjacent compared to phi, right? We don't care about the blue angle. It's all about compared to phi. Okay, good. So using V above, label its x and y components, draw the new position of phi. All right, I think we did that. Good. In terms of V and phi, what is Vx? Well, Vx is an opposite. So Vx, and maybe I shouldn't call it Vmax. It looks like that's going to confuse people, or it's going to just create a new layer to the problem we don't need. So we can just call this, but V is Vmax. We can call it V, since it's an opposite, V sine of phi. Since it points left, we're also going to have to include a negative sign right here because for it pointing left. And so I'll just make a little note of that. Negative means pointing left. And that makes sense for the cup of coffee, right? That it has a negative velocity, because if we look up here, it's traveling counterclockwise, right? According to this. So if that's the case, it's going to the left, so its Vx should be left. Okay. All right, good. Notice that V tangent is the maximum. All right, I tried to point that out. V is V tangent is V max. That was what I was trying to say there. Let me just say it really quick here. V tangent is V max. All right, and is that super important? No, not totally, but I just wanted to point it out because it's going to show up because we're going to have to solve for V here in a second. We're going to get expression for V. Okay, so Vx in terms of pi, radians, F, and T, and A. So what was our expression for phi, right? Because we want to rewrite what we just wrote, but we use sub in something for phi, and maybe also for V max, right? Yeah, we don't have to do both. So, all right, so let's see if we can do this. So we're saying, I think I'm going to rewrite this as Vx as a function of time is equal to, well, for V, let me see, for V here, we have 2 pi f times the amplitude for V max. and that's v. So here we have 2 pi f times the amplitude. And for phi, we have, what do we call phi? What's it? It's 2 pi f times time. Okay, so that's up from above, right? All right, so we're saying this is 2 pi ft. Okay, so let's go ahead and rewrite that then. We are saying then this is going to be rewritten as negative. I'm going to write this in blue because there's too much black here, and blue will stand out a little bit better. Negative 2 pi f times the amplitude times the sine of 2 pi ft. All right, and once again, why do we need this function here of the x velocity, which is in simple harmonic motion in terms of time? The reason we need this, our velocity as a function of time, in terms of frequency and amplitude and time, is that this makes it a lot more of a useful formula for us if we know the frequency, if we know the amplitude, or if we know the time to find the velocity at that time for any object in simple harmonic motion, right? That's the idea, that this coffee cup, its shadow that's oscillating left and right, back and forth, that there is you can the same simple harmonic motion that the shadow is undergoing in that formula is valuable for other types of simple harmonic motion, is what we're going to see here. Okay, and once again, if you know the calculus, then maybe you know why this equation maybe just makes sense in terms of derivatives, and so anyways, but if you don't, you can kind of see where it came from, right? And understanding it in that regard. Okay, so down here I have complete the equation. I think I just have this written a different way because you'll see it in the book sometimes with Vmax. We do know that Vmax is equal to this 2 pi f times the amplitude. And so what I'm saying here is we can rewrite this down here as just that, right, with Vmax being the green part right here. So just subbing in Vmax for 2 pi f times the amplitude. And you'll see that in the textbook. That's kind of where that's coming from. And once again, reminding ourselves that Vmax is equal to 2 pi f times the amplitude. Okay, good. Good. All right. One last part here to this. Okay, so this object is moving in circular motion, this coffee cup. Let me see if I can go ahead and color it again. A little brown there. I don't know. It's just the color I'm using. I don't go with it. It's working. All right. So this this coffee cup has an acceleration because it's in circular motion. And is this acceleration tangential or centripetal? And we should say centripetal for circular motion, right? And centripetal acceleration is always center seeking. That's what the word means. It actually showed up last year on the AP test where you had to talk about centripetal acceleration and identify it as center seeking and not center fleeing. Center fleeing would be centrifugal with a fugal with an F and doesn't exist, right? That's just inertia. That's just an object, its tendency to want to move off in a straight line. But as far as physics is concerned, it doesn't exist, even though we like to talk about it existing sometimes. It's just the apparent, it's the feeling we get by wanting to travel in a straight line, right? An object in motion stays in motion unless acted upon by an external force. It's inertia. So centrifugal force comes from that feeling we get from wanting to move in a straight line. But it takes a center-seeking acceleration to travel in a circle, or a center-seeking force. So we call it centripetal acceleration and centripetal force. All right, so we have A sub c is equal to, ooh, how are we going blue? Yeah, v squared over r. All right, sub in v max for v. We can also sub in amplitude for r, right? I mean, I think we should do that. Okay, let's go ahead and do this. So we are saying then that A sub c is equal to, what was v max? Was it 2 pi fa? Yeah, 2 pi f times the amplitude. Okay, so we're subbing in 2 pi f times the amplitude, and we are going to square that, right, because that's v, and then the amplitude is r, so we have that right there. We can see now if we divide away the amplitude, we on the bottom with one of the amplitudes on top, I think we're going to end up getting, oh boy, something like this, right? Which is the same as, which is also equal, and you can write it like that, or you can write it like this, 4 pi squared f squared times the amplitude. And either of those are okay. I think the one that shows up more so in the textbook, and the one we're going to use is going to be this one, more often than not. All right, so anyways, 2 pi f squared times the amplitude. All right, and this is what? This is acceleration at its maximum. This centripetal acceleration, that is this. This is A max. Because we want to know how much this acceleration points in the x direction. Remember, when we started this, it was all about the x displacement, or the x position, the x velocity. And once again, we want the x acceleration. So we just want a piece of this. So a piece of this acceleration that points like that, right? We know the acceleration points down and left because it points towards the center. So we have A doing that. That's A max right there. And that is this right here, right? And so I have AX being right here and AY being right here. And in terms of phi, I think we can see that phi is that angle right there. So that's actually very nice and very simple to draw that in. That is this angle right here. Let's maybe give it a little color so it stands out a little bit. So I'm saying, oh, I'm going yellow. All right, I guess I'm going yellow. It is that angle right there. And okay, so that we have something like that. 90-degree right triangle. Okay, let's make the 90-degree angle red. All right, so, okay, so obviously a hypotenuse across from theta. We don't care about AY, but it's the opposite. AX is the adjacent. So we're thinking cosine here, right? That we can solve for AX. It's going to equal the hip cos the angle. So A cos, well, the angle is actually phi still, right? So I just got to remind myself that. So that's phi. So we're saying AX is the hip A times the cosine of phi. Should have stuck with blue. Dang. Just stands out a little bit better with all this writing. And one other thing I forgot was it's pointing to the left. So it's negative. And remember, that's situational right there, right? Based on where the coffee cup is. Could just as easily be positive if it was in a different location. But for this location, we know it's negative. And okay, so complete the below equation. So what we have here then is we have A max, which is the same as A, right? And so we can go ahead and write this. Do they want it in terms of phi? I think we just wrote it in terms of phi. So let's go ahead and make the sub there, right? Let's sub in for phi. This is really 2 pi ft for phi. And so what we're saying then, this is negative A max times, let me go ahead and write this in black so this kind of goes together here, times the cosine of 2 pi ft. That here is an expression for AX, or AX as a function of time. All right. Now, you might say, well, why don't we go a little further? If A max is equal to, what do we say max was? 2 pi f squared times A? Right? So if that's the case, why don't we sub that in as well and just get rid of A max? And so we have an equation that is similar to what we had before. The acceleration as a function of time is equal to negative, instead of A max, we'll put in that 2 pi f squared times the amplitude, right, for A max. And then multiply that by the cosine of 2 pi ft. Once again, if you know the derivatives, then maybe this makes a little more sense where that 2 pi f out front, why it's getting squared. And if you don't, that's fine too. You can just think of it in terms of how we use centripetal acceleration as v squared over r and got that expression. But this is our function that we're going to see in the textbook. Acceleration in the x direction as a function of time, and but also including frequency and amplitude, and allowing us to work with frequency and amplitude and time to come up with the acceleration for an object at a particular time, right? If we know the frequency, if we know the amplitude, we can get that acceleration value at any time in simple harmonic motion. Okay, so good deal. And don't forget the negative sign is just because it is a inverted graph. Yeah, it is inverted from the cosine function. And so that's why there's a negative sign there. It's kind of on this function. All right. Inverted from the position function. That's what I was trying to say. Okay. Negative sign particular to the current. Okay, so, all right. I think that's about it. And now you can kind of look back and see where these three functions, right, that we came up with, this one being this one right here. So where are these three functions? Let's go through and just maybe highlight them really quick here. Let's see, let me pick a color, maybe, I don't know, gray? Gray highlighter? Is that a thing? Let's see if that's a thing. I guess it's a thing now. All right, so we have this position function, position as a function of time in terms of, and for simple harmonic motion, we have the velocity as a function of time for simple harmonic motion. and then we have the acceleration as a function of time. And once again, the book broke this down into this more complicated looking one, and then also this easier one, just so you don't have to think about A max as making it too complicated looking. So you can just use that one, and it's really the same idea. And this one, I think we wrote one with Vmax in it, right? So it's not as bad to look at. And I don't think we had to worry about that for the first one, because the amplitude is just A the whole time. I guess it's the max position, the max distance. So I guess it could be X max, right? You could have X max there for A. And you could write it again. What would that look like? I'm not sure why you would do that, but since X max is obviously the amplitude, but maybe it's not obvious. And so there you go. There's another one right there. All right. Once again, what page in the textbook are these on? These are on page 447. So if you're wondering, if you forget these equations, but I guess something important to realize is they don't have to start with cosine. Position doesn't have to be cosine. Velocity doesn't have to be sine. Acceleration doesn't have to be cosine. And that's tricky to think about. But if the coffee mug would have started at a different location, you might use a sine wave. Because a cosine and sine wave are just shifted waves. So you might start, your position function might be a sine wave. And then if that's the case, then your velocity function is a cosine wave. And then your acceleration function is a negative sine wave. And so that's kind of tricky, flipping between the three. If you don't know how to do derivatives, and even if you don't know, you can kind of get the pattern, right? The derivative of the cosine is negative sine, and the derivative of negative sine is it's just you don't apply another negative sign, so it's just so the derivative of sine is cosine. And so the derivative of negative sine, the negative just stays out front and it becomes negative cosine. So that's kind of the idea. All right. Anyways, so there you have it. All right. Hopefully that's making sense. And that's as tough mathematically, I think, as it's going to get in this class. But just remember, it's all just describing redundant, repetitive motion. And with functions, right? Like how the position, how the velocity, or how the acceleration changes as a function of time. And then being able to work frequency and amplitude in there because it makes the equations a little more flexible and useful. All right, so there we go. Good, I'll have some examples coming at you next for this, and have a good day.